Well, it is a pleasure to introduce Professor Bruna Oréfice-Okamoto. She is a professor at the Universidade Federal de São Carlos, and she will talk about invariants of an isolated determinantal singularity. Thank you very much, Bruna, for accepting the invitation. You can start when you are ready.
Okay, thank you, Barbara, for the presentation. And thank you for the organizers to invite me to talk about my work here. First, I'd like to say sorry to everyone because I'm not participating from of the seminars this year because I'm teaching at the time. So sorry. I will start to participate as soon as I can. Okay. I will change to my PDF. In fact, I will use three telas, and please, if you can't see what's happening, let me know. Okay, I will go there, Barbara. I will stop to see you. Please talk to me if something is wrong. Okay.
Okay.
Okay, so this is a joint work with Juan José Nuño-Ballesteros from Universidade de Valência and with João Nivaldo Tomazella from UFSCar. Okay, if we consider a holomorphic map germ, phi from C times Cn to Ck, we can look at a family of germs phi t from Cn to Ck, such that the phi t is defined by phi t of x is the capital phi applied in Tx. And also, we can look to the family of germs of varieties xt, where each xt is the inverse image of ft of 0 by ft. This is wrong here, okay? So, with a family more or less like this, sometimes we want to study when such a family is constant in some sense. And one way to do this is to relate some number to each element of the family and see what happens when they are all equal. For instance, in this sense, we have the Milnor number, which is defined for an isolated hypersurface singularity. It was defined by Milnor in 1968. It is also defined for ICES by Hahn in 1971, and for a reduced curve by Bushwitz and Groyle in 1998. And in 2013, it was defined the vanishing Euler characteristic of an isolated determinantal singularity, which is kind of a Milnor number too. It is defined for some other varieties with non-isolated singularities, but we are not look to this today. And we have also the polar multiplicities. In 1981, Lee and Tessier defined the if polar multiplicity of a germ of analytic variety with dimension d for I going from 1 to d minus 1. In 1993, Gaffney defined the diff polar multiplicity of an ICES. And also in 2013, we defined the diff polar multiplicity of an IDS of dimension d. Well, and how about the family being constant and the X singularities in family? We have a lot of work about this. In 1976, Lee and Ramanujan, they proved that a one-parameter family of isolated hypersurface singularities of dimension not equal to 2 has constant topological type if the Milnor number of the family is constant. And the same is true for a family of ICES, again with dimension not equal to 2. This was proved by Parameswaran in 1991. And for space curves, the topological triviality of the family was obtained by using an appropriate version of Milnor number by Bushwaite and Groyle in 1980. For plane curves, the mi-constant condition is also equivalent to the Whitney singularity. This result is from Zariski from 1971. In 1975, Briançon and Expeder, they present an example that show that this is not true anymore for hypersurfaces with dimension bigger than 2, bigger than or equal to 2. And in 1973, Tessier proved that a family of hypersurfaces is Whitney singular if and only if the mi star sequence is constant. In 1996, Gaffney studied the Whitney singularity of a family of ices. He showed that the family is X-singular, Whitney X-singular, if and only if the polar multiplicities are constant, all of them. And in 2018, we proved that a good family of IDS is Whitney X-singular, if and only if the polar multiplicities are constant too. Well, this is to establish that we want to know how to calculate these invariants, that they are important. Barbara, is everything okay?
Yes. Yes, very good.
So, if you are working with ices, and the so famous Leibniz formula help us to calculate the polar multiplicity and the Milnor number. We can work in dimension of a vector space over C. I mean, if we have two ices, X and Y, and X is defined by K minus 1 function germs 1 until K minus 1, and Y is defined by the K function germs 1 to K, then the sum of the Milnor number of X with the Milnor number of Y is equal to the dimension of this vector space here. Here, On is the local ring of the analytic function germs from Cn to C, and this is the ideal generated by Φ1 at Fk minus 1, and this denotes the minors of maximal size of the Jacobian matrix of this map, which appears here. Well, what we want? We want to find a way to calculate the invariance of an IDS2. So I will start by defining the things. I will consider three integer numbers, S, M, and N, with this disorder here. And I will denote by capital M, Mn, the set of complex matrices of size M times N. And I will put an S over here to indicate that the matrices here are the ones with rank less than S. Well, it's known that this set is an algebraic variety of the set of all the matrices with this codimension here. The codimension is equal to M minus S plus 1 times N minus S plus 1. It's called the generic determinantal variety. Now, I consider a holomorphic map germ C from Cn to the set of the matrix of size M times N. And I will consider the analytic germ X, the germ defined by the inverse image by psi of this set here, of the matrix with rank less than S. Another way to say this, I just consider the psi as a matrix of function germs. Then I consider the ideal generated by the minors of size S of psi, the X will be the variety of this ideal. Well, we say that such an X is a determinantal singularity of type M and S if it has the codimension equals to the codimension of the set. I'm pulling back here this MMNS. It's like it happens for analysis, né? I consider the inverse image of zero with something of dimension P, the dimension of the target, and this codimension of the target, and I assume that it has the same codimension to be a complete intersection. I don't know if it's clear. Well, if I assume that S is equal to 1, or that the numbers I'm working with satisfies this inequality, that the capital X is smooth in all small x in a neighborhood of 0, then I say that this X is an isolated determinantal singularity. This is what I call an IDS. It includes the case of hypersurfaces and also of ices, because when S is equal to 1 here is just an isis. Okay. So in my PhD, our project is to define kind of a Müller number for this kind of singularity. And we did the vanishing Euler characteristic. To do this, we considered a matrix A in MMN, and we denoted PCA from CN to MMN, the map who takes X to PC of X plus A. And for HA, we denote by XA the inverse image of the matrices with rank less than S by this map that I defined here. Well, we showed there that the Euler characteristic of XA does not depend on A in W, if W is a non-empty zero open subset specific there. And then we could define the vanishing Euler characteristic of the IDS X by this way. I denoted by nu. Nu of X0 is equal to -1 to the dimension of X times the Euler characteristic of XA minus 1. This is the same of the Müller number if you are working with analysis, because this would be the minor Müller fiber. Well, some more definitions. A map germ, capital C from C times Cn to MMN, such that the capital C of 0x is the previous C. It's called the determinantal deformation of my X. And a determinantal smoothing is a determinantal deformation if the xt defined in this way, and I consider the t fixed here. Then the map ct defines a variety, which I call xt, and if it is smooth for all t not 0, then I call it a determinantal smoothing. And in this case, we proved that the vanishing Euler characteristic of X is equal to -1 to the dimension of X times the Euler characteristic of xt minus 1. Well, then we showed that this number, it's a good definition. It's the same that was defined before. If the dimension of X is equal to 0, then the nu of X is equal to this. If the dimension of X is equal to 1, that is, X is a curve, then the vanishing Euler characteristic is equal to the Müller number defined by Beschwitz and Groyle. And in the case dimension of X is equal to 2, then the vanishing Euler characteristic is equal to the second best number of XA. And in this case, I could call it the Euler number. Well, all this was to define the vanishing Euler characteristic of the IDS, the kind of a Euler number. What I want now is to define the polar multiplicity. So I have to work a little bit for this. For a generic linear projection P from Cn to C, and the matrix A in MMN, the number of critical points of P restricted to XA is equal to the vanishing Euler characteristic of X plus the vanishing Euler characteristic of the fiber of P in X. Well, this we can see as a determinantal variety in P minus 1 of 0. So this is what we defined before. And I kind of the Lagrange formula because I can see this in my left hand as the Euler number of P. And this is what is the Lagrange formula for analysis. I put an example. I should have put it before. I don't know. I consider here X the determinantal variety defined by this map here. So X, Y, Z, W goes to this matrix here. You will have to believe me that this is an IDS because we don't have time for this. And it's dimension 2. So I want to calculate the vanishing Euler characteristic of this X here. So I will consider the determinantal smoothing, a determinantal smoothing of F. So I pick a matrix A here, and XT, what is the inverse image of the set of matrices with rank less than 2 by F plus TA, is the determinantal smoothing as we did before. Well, this F plus TA is a 2 by 3 matrix. It has 3 minors of size 2, which we denoted by G1T, G2T, and G3T. And I consider also a linear projection. Well, you remember that the vanishing Euler, I will go back a little bit, that the vanishing Euler characteristic of the IDS is related to the number of points in the singular set of P restricted to XA. So I will calculate the singular set. What's this? I consider the Jacobian matrix of the map defined by P and by the germs which defined XT, this G1, G2, Gt that I have for J1, J2, J3. Né? And then the singular set of P restricted to XT is equal to the variety of the minors of size 3 of this matrix and of the germs which defined the XT. Then I used Mathematica to count the points here, and I get 3. The number of points here is equal to 3. Well, now I want to calculate the other part that appears in this sum. This is the vanishing Euler characteristic of X intersection 2 P minus 1 of 0. But this is a curve, and we know that it's equal to the Euler number of the curve as defined by Bushwitz and Groyle. So you can use this result of Nuño-Ballesteros and Tomazella to show that this Euler number is equal to the Euler number of G minus the j, minus the degree of j, plus 1, where I'm sorry, it's g or j, I don't know, where g from x intersection to p minus 1 of 0 from the curve to c is a function germ with isolated singularity. Well, then in order to calculate this, I will calculate these things here. I pick a g, then the Milnor number of g is equal to the number of singular points here, which I used Mathematica to calculate 2, it's equal to 4. And the degree of g is the cardinality of a generic, of the inverse image of a generic value, which is this thing with Mathematica 2. This is equal to 3. And then the vanishing order characteristic of x, which was this, is equal to this thing. It's equal to 1. So we have this way to do the things, but we are not very happy with this count of points in mathematics. We want to see as some dimension, something more easy to do. Well, also, if P is a generic linear function and the dimension of the IDS is equal to G, then we proved that the Euler obstruction of X is equal to -1 to D minus 1 times the vanishing order characteristic of X intersection P minus 1 of 0 plus 1. Well, why I am talking about this now? I will go back again to the theorem. Here, this theorem. So I related this number to the Euler obstruction of the variant X. And then the Euler obstruction does not depend on this P. And this proves that this number here then does not depend on P. And this is what I will call the polar multiplicity of X. So the polar multiplicity of X is equal to the number of points of the singular set of P restricted to XA, where P and A are generic. So also, then you have all the polar multiplicity, because until D minus 1 it was defined before. Then we proved that if the dimension of X is equal to D, then the vanishing order characteristic of X, there is no 0 here, of X is equal to this thing, this alternated sum. And remember that the Euler obstruction of X is equal to this. Well, what this theorem says to us is that if I can calculate the polar multiplicity of an IDS, then I can calculate all the invariants I was talking about until now. So this is our goal. Sorry. Well, so let's see how we calculate the MD. Remember that MD is equal to the number of critical points of P restricted to XT. Well, what's this? If I consider a projection P from the singular set of P restricted to XT, I don't know why I'm using two ways of notation. It's this S and this sigma is the same thing. It's the canonical projection P of X is equal to T. Then this number is equal to the number of points in the inverse image of T by pi. Well, that is, it is the degree of this pi here. But the degree of this pi is equal to the Hilbert-Samuel multiplicity of this ideal. Here, where I put this y, is S of P restricted to xt. Well, if X were an ICES, then this Y that appears here would be Cohen-Macaulay. And therefore, this would be this dimension here. It's, again, the Legros formula. But for general IDS, if it's not an ICES, this is not Cohen-Macaulay. Then we stop here. We can do this step here. Well, what do we do then? To research, to get around this result, we resort to the Turina transform. What's the Turina transform? I will put the definition here, but I will do an example in a minute. So I consider C from Cn to MMN, the holomorphic map jar, defining my ADS. That is, X is in this way. So the Turina transform of F is this set here. Here, this X0 is the regular part of X. So is the XW in the regular part of X times the Grassmannian variety, such that this W is the kernel of PC of X. I can see PC of X as a linear map. Okay. Oh, sorry. The projection on the first factor makes this Turina of X a transform of X. And what's the advantage? This can be an ICES. And when this is an ICES, we can do like before. So the theorem that we are looking for is this one. I consider X the dimensional IDS in C capital N of type M and T. This means that X is given by a map from C capital N to the set of matrices with size M and N, and is the inverse image of the matrix with rank less than T. And I assume this hypothesis here, and I just say what's bigger, M or N. If it's not the case, I just take the transpose of the matrix, whose Turina transform is an ICES. Then we proved that the dipolar multiplicity of X is equal to the sum here. The dimension as a C vector space of this local ring here over this ideal. What's this ideal? This ideal is the generators of the Turina transforms, and the Turina transform is equal to the variety of this plus ER plus 1, this ER here, of the Jacobian matrix of H1, HR, P, where P is a generic linear projection. This IR plus 1 denotes the minors of size R plus 1 of this matrix here. And then I can calculate the MD as a sum of dimension of vector spaces as I desired. Before the example, I have a remark. If X were an ICES, then the Turina transform is equal to X. And therefore, the above is this, what we knew. This is the definition of Gaffney. Well, let's do an example. So, this is PC. I consider PC from C4 to M3, 2. The map germ defined by this way. So is this, I take X, Y, Z, W to this matrix here. And I took X, the determinantal singularity, defined by the minors of size 2 of this matrix. This is an IDS, and it is dimension 2. Well, in this case, we will consider the Grassmannian 2-1, which is just P1. And I will consider 2 parameterizations. First, I take an A to 1A, and the other one, an A to A1. I have to work in both of them. So I'll do first the first. So in the first one, the Turina transform is defined by this way, né? This has to be in the kernel of this. So is the Turina transform is the variety of this product here, né? So x plus y plus zi, oh my God, x plus y plus za, and z plus wa. It is an ICES, and I choose a projection here, P, and then by our theorem, we have to calculation the dimension as a C-vector space of this thing here. Now, this is local in X, Y, W, and Z, and global in A. Here, the H is this ideal here, and JHP, it's the Jacobian matrix of this plus this. I took the minors of size 4. And then this is 3. Now I have to look on the other parameterization. So I was with 1A, now I do A1. I get this, the Turina transform is this. It is an ICES 2. Well, here I have to remark that the points of the form A1 with A not 0 was counted before. Therefore, I just work as a germ at 0. And then I do everything local. So the dimension is equal to 0. And then the polar multiplicity is 3 plus 0, which is equal to 3. This was our example. So I put another one. Do I have time? What time is it? Okay.
Yes, we have time.
Okay. Here I consider another example. I took this F from C5 then to M23, and I consider a deformation of it. So a capital F, I just put a plus T x2 y2 here in this element of the matrix. Then by it T, I have an IDS here. An IDS of dimension 3, and the Turina transform is an axis. So I will do the same thing. I consider 2 parameterization, A1 and 1A and A1. In the first, the Turina is given this way. I just make the product here. I took this P, and then the dimension of this space here, I calculated with singular, is equal to 12. On the other parameterization, I consider it local, and the dimension is equal to 0. And then the polar multiplicity is equal to 12. Well, in order to calculate the vanishing order characteristic and the other obstructions, I have to calculate all the other polar multiplicities. M0 is the singular calculator, just put the mult. So I have to look for I equal to 1 until D minus 1. So this was defined as the multiplicity of the singular set of P restricted to the regular part of X. Sorry, that's not mine. Where P from Cn to Cd minus 1 plus 1 is a generic linear projection. Well, If X is given in this way, then this set that appears here is equal to the singular set of P restricted to X minus the singular set of X. And this is equal to V, the variety of the Sing P minus the variety of Sing X, where who is Sing P? The ideal which defines the singular set of P restricted to X, which is the ideal which defines X plus the ideal generated by the minors of size codimension of X plus G minus 1 plus 1 of the Jacobian matrix of the ideal which defines X and P. And Sing of X is the ideal which defines the singular set of X, which is the ideal which defines X plus the minors of size codimension of X of the Jacobian matrix of the map which defines the ideal which defines X. It's a mess. Well, then what we want is this. And this is equal to the variety of the saturation of this quotient here. Well, therefore, the MI is equal to the multiplicity of this ideal here. Okay? And then I have an example, but now I hope I don't make a mess. I will go to singular. Let's just take note. X, Y, Y, Z plus Z, W. I will consider this map here, the map I was working for. Then I put here. Can you see?
Yes.
Yes. I put here, I wrote here what I was Singularity to do, like a proc. So I will calculate any one of the matrix F. So I define the ideal way to define my IDS is the minors of size 2 of my F. Then here I took two generic linear projection, and I consider J1 the Jacobian matrix of this I here plus P. So the ideal Sing P, which defines the singular set of P, is equal to Y plus the minor of size 4 of this matrix here. And also I have to work with Sing of X. And then I consider the Jacobian matrix of I, and the ideal Sing X is equal to I plus the minors of size equal to the codimension of X of this matrix here. And then I do the saturation, and the number that it will return is the multiplicity of the radical of the saturation. And this is it. Let's put a singular. I hope it works. I just open the library here. I defined the ring before, then I put the matrix. I'll call it F3 by 2 is equal to X, Y, Y, Z, and Z, W. We have the matrix. Then I will ask it to do the M1 of F. It does, and it's equal to 4. Okay? Barbara, okay?
Yes, yes, okay.
I will skip a lot of things because I was afraid that singular wouldn't work. This I did all there. Here. Well, now I have another example, and I want to calculate the vanishing Euler characteristic of A. So I want to calculate all the polar multiplicities and the vanishing Euler characteristic. I put it as singular too, and we go there. Then the mu1 is this, like the one we did before. It's 4, 2. Let's see here how I calculated the M2 in this case, it's the MD. I wrote here, well, so I defined the singularity. Then you remember that I have to work with two parameterization of the projective space. So I called first the ring that I called R1. I put X, Y, Z, W, A. So local in the first 4 and global in the last. I recovered the matrix F, and I defined the Turina transform. Then I took the generic linear projection, calculated the Jacobian matrix of the Turina transform plus the projection, and the minors of size here to generate the Turina transform. I have three functions. So the minors of size 4, and calculated the dimension as a C vector space of this part here. I called it M1. Then I do it again with the other parameterization, but all local now. Did the same thing, the same projection, and call it M2. And then I just did M1 plus M2. This will return my MD. So it's maximal multiplicity. So is F stir, it is 5. Then, if I wanted to calculate the other variance, the vanishing Euler characteristic and the Euler obstruction, the vanishing Euler characteristic, I called it nu. I just calculate the M2. I calculate the M1 with the other two procs. The M0, the singular already calculated, and then I do the alternated sum, which defines the vanishing Euler characteristic. So if I put here, F, it will do it, it's 3. And the Euler obstruction, I just use the relations. It's the vanishing Euler characteristic plus 1 minus M2 in this case. I called it 2 minus 1. And this is all together. I skip everything again because I was really afraid. A lot. Well, and here is the final of the example. And this is it. Thank you.